Okay, so let's take a look at doing weak acid and base pH problems. So here again, we've got our strong bases up here at the top. And we've got our strong acids over here at the top. And we know that anything not on these lists will be either weak bases or weak acids. And so you'll also notice that we have a couple of other things up here. We have the Ka, which is the acid dissociation equilibrium expression. We have Kb, which is for base dissociation. And then we also have this expression over here that relates the two. It just says that the Ka and the Kb, we multiply those together, that's going to equal Kw. Okay, so these problems are a little bit more complicated than strong acids and strong bases. We'll note here we have HF. It's an acid because it contains a proton. That's generally true. And we're given a Ka value for it and a concentration. So in the previous problem, in the strong acid problems, we can assume that the HF concentration is equal to H plus. In this problem, that's not true. And instead, we have to consider this equilibrium that's going on. So we start by writing out the equilibrium expression. And you'll notice that since this is an acid, it matches this form over here for the acid dissociation equilibrium constant. And so to figure these problems out, we start by writing out a Rice table. And we just say that we don't know what this hydronium concentration is going to be. We know wherever it's going to come from is HF dissociating. So some of this is going to dissociate and contribute to H plus. We know it's not going to be all of this because that's what a strong acid problem is. We know it's going to be some amount. We're going to call that amount X. And that allows us to write out all of our equilibrium concentrations in terms of X. So we have HF is equal to 0.1 minus X. And then H plus is equal to X. And F minus is also equal to X. And so we can write out an equilibrium expression for this. We can say that Ka is equal to F minus times H plus, so the products over reactants. We put this over HF, and then we can plug in these values that we've expressed over here algebraically into this mass action expression for the acid dissociation equilibria. And since we know Ka, since it's given to us in the problem, what we end up with is one equation with one unknown, which we can solve. So remember, you can solve equations. You can solve for as many unknowns as equations that you have. So one unknown, one equation, and we can solve. And so we end up with this expression here. So if we work through all the algebra here, you can get this into a quadratic form and just solve it with the quadratic equation. So if you take this and you multiply it over here and do some rearranging, you can end up with an equation in the quadratic form. But an easier thing to do is to recognize, or hope, I guess, that if the equilibrium constant is small, so K here is less than 1, much less than 1, that means that X will be small. That's sort of the hope here. If K is much less than 1, then X will be small. It's not always true, but it's usually true. But this allows us to just make this approximation and say, we can say, well, if X is really small, then 0.1 minus x is probably going to be equal to about 0.1, meaning that, 0.1 is going to be much greater than x. And that simplifies this equation over here to where now we don't have to worry about the quadratic, and the answer is just going to be x is equal to 6.6 times 10 to the minus 4 times 0.1, and we want to take the square root of that. And so I'll punch that into my calculator here. We have 6.6 times 10 to the minus 4 times 0.1, and then we want to take the square root of that, and we end up with x is equal to 8.1 times 10 to the minus 3. So remember what the question is asking for, though. It's asking for the pH, the POH, the H plus, and the OH minus concentrations. We've solved for x here, and remember x was a stand-in for, or x was something that allowed us to, that we were using to calculate the concentrations of these different species at equilibrium. The only one we're really worried about is the hydronium concentration, which is equal to x. So we can take this and just say, okay, H plus is equal to 8.1 times 10 to the minus 3. That's exactly what I've said here. And so that takes care of this. And then I can just jump between all of the other different things that we need using some really simple math. We can say that the pH is equal to the negative log of x, which is equal to somewhere around 2.1. And the POH is going to be equal to 14 minus the pH, which is 14 minus 2. My calculator is faster than my brain. That's 11.9. And then finally the hydroxide concentration, which we can get by taking 10 to the negative POH, which is equal to hydroxide. And that is going to be equal to 1.3 times 10 to the minus 12. And so then we've solved for everything in this particular problem. Yeah, let's take a look now. I'll come back to when that approximation that we did for 0.1 minus x, when is that valid or invalid? I'll do a little, after I work both these problems, I'll explain when. It's valid for both of these, but let's work through the chemistry, and then we'll come back to some of that math. Okay, so here we're asking about the concentration of pH and all these different types of things, these pH-related types of ideas, but for fluoride instead of hydrofluoric acid. So note here that fluoride is the conjugate base of hydrofluoric acid. The conjugate base of a weak acid is just a weak base. So that's one way to know it's a weak base. It's also not on our strong base list. So those are both reasonable ways to recognize that it's a weak base problem. So we write out, for bases, we write out base, this different expression, which is showing that F minus, once it reacts with water, produces OH minus. And so this is different from the acid dissociation constant where we're generating H plus. And so we can do the same thing over here that we did for the other one, which is write out a Rice table. And we can say, well, we're starting with 0.1. So now we're not looking at calculating H plus anymore directly. We're going to calculate OH minus, but we can ultimately get pH from that. The change is going to be some loss of X. We're going to gain some amount of HF, and we're going to gain some amount of hydroxide. And so we can write this out like this. And then we have this expression that we can write for the equilibrium, which is that the Kb is equal to OH minus times HF divided by F minus. So again, just products over reactants. So note here, so F minus is the conjugate base of HF, but note that the forward reaction for this generates H plus, and that when we're writing the base expression out, so this expression for Kb, there is no H plus in it. We have OH minus. So the reverse of this reaction is not this reaction. They're related, but they're not the reverse of one another. This is not running that reaction in reverse. This is a different type of reaction, or we think about it differently, or we're generating OH minus. And so Kb, you'll notice, has hydroxide in it, whereas Ka has H plus in it. And so these things are not just simply, Kb is not simply 1 over Ka. It's related in a different way. And you'll also note that we're not given the Kb here, but we do know the Ka from this previous problem. And so if we want to relate Ka and Kb, we can do that through this expression, which is just that the Ka times the Kb equals the Kw. So if we want to calculate Kb, we just say Kb is equal to Kw divided by Ka, which is equal to 1 times 10 to the minus 14th divided by 6.6 times 10 to the minus 4th. And we end up with a Kb of let me punch it in my calculator. We've got 1 times 10 to the minus 14th, and we're dividing that by 6.6. So Kb is equal to 1.5 times 10 to the minus 11th. Okay, so now the workflow for the problem is pretty much the same. Here we've got F minus is equal to 0.1 minus X, HF is equal to X, and then what we're really concerned with, specifically because of what the problem is asking for, which is all these different things, OH minus, POH, etc., is the OH minus concentration, which is itself equal to X. So I come back over and I solve this in a virtually identical way that I did for the acid problem, at least in terms of the algebra. I say 1.5 if Kb is equal to 1.5 times 10 to the minus 11th, we can plug in all our values. So this is equal to X, this is equal to X, OH minus and HF are both equal to X. And then down here, we're going to assume that 0.1 minus X is well approximated to, we're going to say that's approximately equal to X times X over 0.1 for the same reasons that we could do that in the last question, which is that Kb is a very small number, so we know X is going to be small. And this allows us to calculate this out much more easily than using the quadratic formula. We can write out an expression that's just that X is equal to 0.1 times 1.5 times 10 to the minus 11th and take the square root of it. And we come out with an extremely small number of X equal to 1.23 times 10 to the minus 6. And so now we want to take this and we want to actually use this to solve whatever the question was. The question was asking about the pH, the POH, the H plus and the OH minus concentration. So I come back over here and I remember that the whole reason we were doing all this was to solve for X so that we could take it and plug it back in to these relationships that are developed over here algebraically. So I know that X is equal to 1.23 times 10 to the minus 6, and OH minus has a relationship to that. And in this case, it's just exactly equal to X. And so my OH minus concentration is equal to 1.23 times 10 to the minus 6 molar. So we don't have to worry about solving these parts because the question doesn't ask us for either of those concentrations. It's just asking about the pH and the POH. All right, so we've solved OH minus. We can solve for H plus. A number of different ways. One is to recognize that this is always true. So OH minus times H plus equals Kw. And so our hydronium concentration is just equal to Kw divided by OH minus. And so that's just equal to 1 times 10 to the minus 14th divided by 1.23 times 10 to the minus 6th. And we come out with an answer of H plus equaling 8.12 times 10 to the minus 9. And so we can kind of plug this in over here. We're doing our bookkeeping. And then pH is equal to the negative log of that number. So negative log of H plus, which is equal to 8.09, which makes sense because we'd expect it to be a little bit basic. And the POH is just 14 minus the pH, or the negative log of the hydroxide concentration, however you want to do it. And that's equal to 5.9, which makes sense because, again, the solution is basic. So we expect POH less than 7 and pH greater than 8. Okay, so that's generally how you work these problems. If you know hydroxide concentration or pH, or H plus or POH, any one of those, you can go between all 4 of them. The main thing that we have to do here that's different from the strong acid, strong base stuff is we have to start out with dealing with these equilibrium expressions, which you can see adds on a significant amount of work to these problems. Okay, coming back to this idea of 0.1 minus x, how do I know that this is okay? So in these workflow for these problems, we'll write out these equilibrium expressions and we'll come out with something like this. So we end up almost with this minus x term all the time. So we start out with some amount and we subtract x from it. And we end up with this expression over here, 0.1 minus x in the denominator. And we want to solve this, but we don't want to have to deal with a quadratic equation. So a lot of times we just take 0.1 minus x and we say, well, that's approximately equal to 0.1. What we're saying there is that whatever x is so small that it's insignificant compared to 0.1. And so how do you know if that assumption is true? Well, the assumption is likely to be true if whatever the equilibrium constant value is really small, because that's literally an expression of how much the reaction is going to lie towards the products. So it's in effect telling you how large x is. So if the reaction lies far towards the product, then x would be really large and k would be really large. But if the reaction lies far towards the reactant, then you're not going to form a whole lot of products over here, so we expect x to be really tiny. The main thing is that it's small relative to whatever the starting concentration is of the reactant. And we don't necessarily know that until we solve the problem. So what you can do is you can make the assumption that x is small. And now I've got 0.1 in the denominator. Solve for x like I did here. So I've got x. And then actually go through and see how well it compares. So, whether or not this expression over here is true or not depends on how precise your answer needs to be. But as a general rule of thumb, if x is less than 5% of whatever your initial concentration was, so in this case, like, how do I want to say that? I guess, yeah, initial concentration. So it could be for HF or it could be for A minus. It doesn't really matter. Then your assumption is valid. So if we're trying to compute that, we can just take x, this value here, and we can divide it by whatever the starting concentration was. So that's this number here, 0.1. And we want to express that in terms of percentages. And so what we see is, this is going to be a really small number. Which is much less than 5%. And so we know that our approximation is valid. And so if you want to kind of like make sense of this in your mind, why does it matter if it's 5%? What we're saying is 0.1 minus x in this situation will be equal to 0.1 minus 1.23 times 10 to the minus 6. And if we actually punch through the numbers on that, what we end up with is 0.099998777. And so this is approximately equal to 0.1. Like if your calculator spits this out, you're not going to be too freaked out to round it up to 0.1. And that's really where the approximation is coming from. It's saying whatever we're subtracting out is so small that it's irrelevant. But if you need to put a hard stop on where that cutoff is, we can say, well, if it's less than 5%, then we're fine. Because that means that this number is not going to change by more than 5% once I subtract x from it. And so within most precision for most instruments that you can measure on, 5% is a pretty good number. You usually can't get much better precision than that, so it doesn't matter if your approximation is worse than that. So that's how the approximations work. But this is the general workflow for these problems: is set up an equilibrium, do some algebra, and then ultimately that allows you to calculate H plus, or in the case of bases, OH minus, and then you can use that to calculate all the different parameters: pH, H plus, OH minus, and POH.